Hi everybody, Professor Jamer here, and today we're going to be talking about topic 11, also known as relative motion. So whenever we have relative motion, we always have something like a boat moving with respect to current, we have a plane moving with respect to wind, and we have the direction that we want the plane or person or boat to travel, and then we have to think about how the current interacts with our object or our person, and how we counteract the effects from current and wind in order to go the direction we want it to. And we all know that if we are riding a boat and we want it to go due north, we can't just travel due north with respect to the boat, because we might have current that will affect the way that our boat travels. So here we're learning how we add the vectors together in order to determine which direction the boat really needs to go in order to go due north. And so we talk about a couple of things here. So let's just draw a scenario where I have a person on the bottom who wants to go due north. Well, let's imagine that I have another person on the other side of the bank that's watching. Those are his binoculars. And so what the person who we call the observer sees is the overall direction of travel. And they also note the direction of the current. So let's just say, for example, we have a current that is going due west. So this is the direction, so the direction of travel is the velocity of the current with respect to ground. So that's what our VCW or VCG means. So this is the velocity of current with respect to ground. And then we mark the vector that we want this person to go to, VPG, which is going to be velocity of person with respect to ground. Here we are talking about ground in terms of the observer, since the observer is standing on ground that isn't moving. So then we're going to draw a third vector, which is essentially the direction that the person needs to go with respect to current. So this is VPC. So VPC is the velocity of person with respect to current. So here, our person knows that he or she needs to travel in a northeast fashion in order to cancel out the contribution of the current with respect to the ground. So if we were to add up these vectors, here what we have is that VPG, so the overall resultant is the direction of the person with respect to ground. And we know that's going to be equal to VPC plus VCG. So here, how do I know I need to set up my vectors in this way? Well, I have VPG, VPC, and VCG. I always know in relative motion if I'm adding our vectors correctly is if I have this with respect to current or wind or whatever we're moving through. If I have these two little C's right next to each other. So if these two C's aren't next to each other, then I know that I set up everything incorrectly. And so what this essentially does, it means that I'm canceling out the effect of the current in order to get the overall resultant, which is right here, the velocity that the person is moving with respect to ground. And so that is the overall direction that I need the object or person, boat, airplane, whatever it is to move with respect to ground. And so that is always my resultant. So now we can look at frames of reference. So this slide may seem a little confusing at first, but it all makes sense if I were to talk about something a little more abstract. So let's imagine you are riding in a car and you're in the back seat, someone else is driving. So let's imagine right here is you, and you are throwing a ball in the air. What you see is that the ball is moving directly up and then it's coming down. The caveat here is that we have the velocity of the car, and we know that the car is moving. If we had somebody outside of the car, what they see is that you're throwing the ball to, in this case, the northeast, and the ball is coming down right here. So what you see and somebody standing on the ground sees is slightly different. And that is essentially all what relative motion is. So here what you'll see is that you're going to be in a car, a boat, a plane, and there is going to be an extra added velocity that will differ from somebody else's point of view if they were on the ground. And so let's work on an example problem. So let's just say we want to describe the velocity of a plane relative to the ground in two ways. We want to use a coordinate axis and unit vectors, and as a magnitude and an angle. So here we want to find V, P, G. So this is our resultant. We know that V plane with respect to air, so we see that the plane's airspeed is 300 miles per hour. And we see that the wind blowing, VAG, is going to be 60 miles per hour. So these are just the overall magnitudes, because here when we look at the actual diagram is that VPA is moving to the east and then the air is moving down towards the ground. So then if I were to add directions into this, I know that this is positive since it's moving due east. But then if I were to look at the diagram, I see that the air with respect to ground is negative. And so let's remove this and this. And then I see that the plane with respect to air is moving in the I hat direction, and this is moving in the negative J hat direction. So just like what I did before, I have VPG, VPA, and VAG, and I want to figure out this value, and this is going to be the overall resultant. And whenever I set this up, I have VPA plus VAG, and then I see that I have the A in between, so I know I set it up correctly, and then I can add the two systems. So here I have VPG is going to be equal to 300 I hat minus 60 J hat miles per hour. So this is how I can figure out part one. So this is coordinate axis and unit vectors. So for part two, what do I need to do? Well, here I need to figure out the magnitude and angle. So I know here my overall magnitude of VPG is going to be equal to the square root of 300 squared plus negative 60 squared. And so I get an overall magnitude of 306 miles per hour. And if I wanted to figure out that angle, this is going to be theta. If I want to figure out theta, I can do that by taking the opposite, which is the VAG over VPA. So then I have theta is equal to the inverse tan of VAG divided by VPA So overall, my angle theta is going to be 11.3 degrees, and then I have to give it an overall direction. And so here I see that the plane is moving southeast. So I'm going to say it's 11.3 south of east. And so that is how I can do this problem. And so let's take another gander at something similar. So here, what is the plane's ground speed? So here I see that the plane's airspeed is 300 miles per hour and the wind is 60 miles per hour. So here I still have that the velocity of the air with respect to ground is going to be equal to negative 60 j hat miles per hour. And I want to find VPA now. And here I'm given that VPG. Oh, wait, I just mixed that up. Oh, I still want to find VPG, but now I have VPA is going to be traveling at an angle here. So then this is going to be 300 miles per hour. But I don't know the angle theta. So we need to find VPG. But in order to do that, what do I need to do is I need to figure out this angle theta first. So how do I find the angle theta? Well, in this case, I can find theta by saying that using SOHCAHTOA. So here I have opposite and then I have the hypotenuse. So then I know that's going to be inverse sine of opposite, which is VAG, divided by VPA. So here I get an angle of 11.5 degrees when I plug that in. And now I can split VPA into components. So whenever I get this type of problem, I need to split up all my vectors in terms of components rather than talking about their magnitude. So here I have VPA is equal to 300 cosine of 11.5 I hat plus 300 sine 11.5 j hat. So if I want to find VPG, I'll use the same resultant as I got before, which is going to be VPA plus VAG. Only now I have an X and Y component for VPA. So then I get VPG is going to be equal to 300 cosine 11.5 degrees plus 300 sine 11.5 minus 60. I have to add in the j hat and the I hat here. And then whenever I were to go about and figure out the overall components, I see that my I hat is going to be $293.97 I hat, and then plus $59.9 minus 60 j hat, which overall goes to 0. So I'm only left with an I hat component for the velocity of the plane with respect to ground. And I can talk about this in terms of magnitudes. And I can say that this is my vector representation. my magnitude of VPG is just going to be 293.97 miles per hour. And then my angle is just going to be due east. So this is how we can talk about our solution. So anyway, we can say that in this solution, our ground speed is less than 300 miles an hour, since here we have the wind is kind of helping us out in a way. So here the plane's ground speed is less than 300 miles per hour because the plane is now flying partly into the wind, and so it doesn't have to overcompensate for the wind here. So that is topic number 11, relative motion. If you have any questions, comments, or concerns, please reach out.